In this video, we're going to look at solving limits that deal with positive or negative infinity. And these are broken up into two kinds of limits. They are limits as x approaches positive or negative infinity, or limits that as x approaches a number will yield some kind of unbounded behavior. And to start with, we're going to look at the limits as x approaches positive or negative infinity. And these are basically in behavior limits because as x increases or decreases without bound, that is meaning what is the graph doing is you're going way off to the right or to the left. And what this limit's going to equal is the behavior of the y values. And they could be approaching a singular number, or they could be either increasing or decreasing without bound as well. Now, in this video, we're going to look at really two kinds of functions with these in behavior limits. We're going to look at polynomials and rational functions. Now, recall the polynomial in behavior rules from Algebra 2 or pre-calculus, where I can determine the in behavior of a polynomial function based on the leading term test, which says that if a function is odd, so polynomial is an odd degree polynomial, that if the leading coefficient is written in standard form is positive, that means that the right side will go up and the left side will go down, which means that in terms of a limit, odd degree polynomial, the limit as x heads towards negative infinity, the limit will equal negative infinity as well. And as x approaches positive infinity, y will approach positive infinity as well. So the same thing applies if it has a negative coefficient. It just basically reflects that graph over the x-axis, which means left side up, right side down. If I have a polynomial that is of even degree, that means left and right sides will point the same direction. So if it had a positive coefficient of the highest degree term, both left and right sides would go up. If it was negative for the coefficient, both left and right sides will go down. For rational functions, we had three kinds of characteristics. Now, if I had a rational function that was comprised of two polynomial functions, where I had a degree of x in the numerator and degree of x in the denominator, we could compare the sizes of those degrees in terms of was it top heavy, bottom heavy, or same degrees to figure out what the end behavior was going to be. So if the degree of the denominator, we'll start here in the middle of the table. If the degree of the denominator is larger, like a prime example would be x minus 1 over x squared. It's considered to be bottom heavy in terms of the rate of growth, meaning that as x increases or decreases without bound, the denominator is going to have a much larger value than the numerator. And because we're talking about division, it's going to be approaching a value of 0. So if the denominator has the larger degree, it'll have a horizontal asymptote of y equals 0, basically meaning that the limit of that function will equal 0. If the degrees are the same, so if I had x minus 1 over x, so same degree, it will also have a horizontal asymptote. And it's going to be the ratio of the coefficients. So actually, let me change this problem to be 3x minus 1 over 2x. So the horizontal asymptote would be y equals 3 over 2. Now, if the degree of the numerator is larger, it's not so easy. In fact, there won't be a horizontal asymptote. And an example of that would be x squared minus 1 over x. And so if this is the case, and I have a function that is top heavy, I would look at the quotient of the two highest degree terms and simplify it. And then I could determine what the ends would do. So this would reduce down to some kind of polynomial function. Then I could say, hey, right side goes up, left side goes down in that case, and I could write my limits. But main thing, if it's bottom heavy, y equals 0, same degrees, ratio of coefficients. top heavy is going to be positive or negative infinity. Now, if I have a rational function, or in fact, let me take that out. If I have any function and the limit as x heads towards positive infinity or negative infinity is equal to a number, that is the definition of a horizontal asymptote. So if the end behavior limits equal a number, that means you have a horizontal asymptote for a function. So let's do a couple of examples here. So look in here at this first one, the top left. The limit as x heads towards negative infinity of 2x squared minus 3. And you can't necessarily just put negative infinity in because it's not a defined value. So we need to look at, well, in my head graphically, what's going on here. I have an even degree term, positive coefficient. So left and right sides are both going up, which means that the limit as x heads towards negative infinity would be the left side. And this graph is going to be increasing without bound. Now, technically, the limit doesn't exist. However, I could describe this by using the infinity symbol saying it's increasing. So technically, it doesn't exist, but we would prefer to use infinity so that way we know what the graph is doing. Now let's go to the next one. The limit as x heads towards positive infinity for this polynomial. Now, this polynomial is an odd degree term with a negative coefficient. According to the end behavior rules for odd degree polynomials, if it's negative leading term, that means right side down, left side goes up. And we're looking at as we head off to the right, and we see that the right side is decreasing, so we can say this equals negative infinity. Next one here, now we have a rational function. And so I'm looking at the limit as x heads towards positive infinity. So I'm asking, what is the end behavior here for this problem? Well, I have a degree 1 in my numerator, a degree 1 in my denominator. And so they are the same degree. So I look at the ratio of the coefficients, which would be negative 3 over 1. Next one here. So limit as x heads towards positive infinity. Okay. End behavior for this rational function that has a degree 2 term in the denominator and a degree 1 term in the numerator. So this one here is bottom heavy. And if it's bottom heavy, that means it's going to have a horizontal asymptote of y equals 0, which means that's what the limit's going to equal. Last one here. So we had the limit as x heads towards negative infinity. And we have the highest degree term in this rational function is in the numerator. So what we'll do is we'll look at this and say, all right, well, the end behavior for this top heavy rational function is going to resemble the same end behavior for the simplified version of it, which I just used the highest degree terms of negative x to the third over 2x squared. Really, in the grand scheme of things, as x gets extremely large in the negative direction, the minus 2 has very little effect. And I'm going to simplify that and say, all right, I could actually simplify this expression a little bit farther to make the limit as x heads towards negative infinity. That would simplify down to negative 1/2 x. And in terms of that, I think about what that graph's doing. Well, it's linear, negative slope. So it's going to behave in that manner. And since we're looking at heading towards the left, because x heads towards negative infinity, we're looking at this left side, which means graphically, this original limit would be heading towards positive infinity. It'd be increasing without bound as you continue to go to the right, or excuse me, as you can continue to go to the left. Now let's look at um, rational functions that are not comprised of polynomials. In fact, it says non-rational functions here. So horizontal asymptotes, I could have exponential functions, trig functions, and so forth. Now, to determine the rate of growth between numerator and denominator, I have a growth rate chart here that talks about what goes from fastest to slowest. And the highest growth rate is the factorial function, which is x exclamation mark. That's the factorial. And then it decreases all the way down until you get to a constant, which basically has no growth rate because it's constant zero slope. And so let's look at doing these problems right here. This first limit, the limit is x approaches positive infinity for sine of x over x. Now that resembles our special trig limit, but our special trig limit is as x approaches 0, so I can't say the answer is 1. I'm looking at my growth rate chart, and the sine function oscillates between -1 and +1, while the x function, which is not constant, it's a linear function, is actually going to continue to grow at a constant rate of change. So it does have a slope. So this is actually going to be a bottom heavy, which means that this answer is going to equal 0. Now let's slide over and look at the next one. So in fact, that whole thing should be in parentheses. Looking at the limit as x heads towards negative infinity of e to the x minus 2x. And when I'm doing the end behavior limits, especially when it comes to exponential functions, you got to pay attention to what direction you're heading because of the effect of the negative exponent. And I break this limit apart, and I have the limit as x heads towards negative infinity of e to the x minus the limit as x heads towards negative infinity of 2 to the x. Well, e to the x when going in the negative direction is actually going to be approaching a value of 0 because the negative exponent moves to the denominator and I have 1 over e to the x. So that's going to be approaching a value of 0 minus, now if I'm heading in the negative direction for x and timesing it by 2, I'm getting a value that's decreasing without bound. So I'd have 0 minus negative infinity, which would make positive infinity. Now let's look at the third one here. So this time we are heading towards positive infinity for x, and I have this this function of 5 plus 2 to the x power divided by 2 minus 2 to the x. And I want to look at, all right, I'm heading way off to the right. What is dominating the value of the function? Well, where x is located, and I'm increasing the value of my exponents, the 2 to the x power, the exponential part, is going to be really dictating the overall value of the function. In the grand scheme of things, the adding of the 5 and that adding of the 2 have very little effect. So I'm almost going to forget that I'm looking at them. So if I simplify this problem, I basically have positive 2 to the x power over negative 2 to the x power. And because they have the same rate, say that equals -1. So they actually have the same rate here. Now, let's look at the same problem, but headed in the other direction. So I'm heading in the negative direction. X is decreasing without bound. And we think of the effect that's going to have for these exponential parts. So if I was increasing the size of the exponent, like we did in the previous problem, the 2 to the x would be dominating the value of the function. But if I'm heading in the negative direction, the value of 2 to the x is actually approaching a value of 0 in both cases, which means that this limit, the farther you go to the left, or excuse me, this function, the farther you go to the left, you're going to be approaching a value of 5 over 2. Now let's look at the next one. We have the square root of x squared plus 3x plus 1 over 4x. And I want to look at, well, how is this behaving? Because it's an end behavior limit, let's go find the highest degree terms, degree 1 in the denominator. And then I have the highest degree term of x squared, but it's actually inside of the squared root. So I'm looking at the limit as x heads towards positive infinity of the square root of x squared over 4 to the x power. Now, the square root of x squared is making the absolute value, x over 4x. Well, we have same degree here. Now, I'm heading in the positive direction, so x is going to be positive in both cases, and so I can look at ratio of coefficients, and that's going to make 1/4. Last example we have for these end behavior limits, we have basically the same function, but we're heading in the other direction. So we had the limit as x heads towards negative infinity of the square root of x squared. I just used the highest degree terms over 4x. And we simplified that to the limit as x heads towards negative infinity of the absolute value of x over 4x. Now, in our rules, we said, hey, if they're the same degree, it's ratio of coefficients. However, we have a restriction here because of the absolute value that the numerator will always maintain a positive sign. And so if I'm heading way off to the left, I'm going to be positive in my numerator, negative in my denominator, which means that this limit is actually going to be, if I go to the left, negative 1/4. Now we're going to look at the second kind of limits that involve infinity, and those are going to be the ones that deal with vertical asymptotes. These are going to be limits where as x heads towards a number, the function of x is going to show unbounded behavior, so it's going to be outputting a positive or negative infinity. So that takes us to what the definition of a vertical asymptote is. Anytime I'm evaluating a limit, and as I head towards the number from the right side, or from the left-hand side, if the limit equals positive or negative infinity, that is the definition and also the indicator that there is a vertical asymptote at that particular x value. So let's do some examples here. I want to find the vertical asymptotes of each function and then determine the limit as x approaches that value from the left and from the right. Now, vertical asymptotes are the values of x that make the denominator equal to 0. And only the denominator equal to 0. And so this first one, we'd have a vertical asymptote at x equals 0. Now, I want to know, well, what's the behavior of that function as I approach x is equal to 0? Now, without having a graph, what I could do is I could make a sign chart here where I have to have, I'm going to put x is equal to 0 on my sign chart. And so I know this is where it doesn't exist. Now, if I'm going to use this method and not look at a graph because maybe this is calculator inactive, I also need to include any zeros. My zeros in this case would be at x equals -3, and so I'd have to include -3 in my sign chart. And if I had a hole, I'd have to include a hole also. So I have zeros and I have discontinuities on this sign chart. Now what you do is you're going to test around, in this case, because I only care how the function is behaving around the vertical asymptote, I'm going to want to get the signs of the function around x is equal to 0. The reason why I put -3 in there is because I didn't want to pick a number that was too far away from 0 to where I'd get the incorrect sign. So as long as I pick a number between -3 and 0, I'll get the true indicator of how this graph is headed. So I'm going to pick -1. If I put -1 in to f of x, I get a positive numerator, negative denominator. Positive divided by a negative makes negative. And then I want to test on the other side of 0. So pick any number bigger than 0, and you would see what the sign is. So I pick a number bigger than 0, +1. Put +1 in for x. I get 3 plus 1, which is 4. Positive over +1. Positive divided by positive is a positive. So I have my sign chart, which means that I can find the value of the limit around both, or around the asymptote. So I'm going to say the limit as x approaches 0 from the left for f of x is equal to -infinity because it goes down. The limit as x approaches 0 from the right-hand side is going to be +infinity. We know that it's negative or positive infinity because graphs show unbounded behavior around vertical asymptotes. Now, the overall limit does not exist. Let's go to the next one. So we're only looking at the limit around each asymptote. Now, I need to factor this problem to see what I have. So if I factor this to find any kind of asymptotes, I'd have x minus 4, x minus 1. And to figure out where the asymptotes are, I could look at that numerator and say, hey, if I rearrange the terms and pull a negative out, that'd make negative times -1 times x minus 1 on the top, x minus 4 times x minus 1 on the bottom. And I don't want to cancel anything out, but what I know here for in terms of discontinuities, x equals 1 as a whole, x equals 4 is a vertical asymptote. Because we want to find the limit around the vertical asymptote, without a graph, we can make a sign chart, put our discontinuities and our zeros on there. Well, all we had were 2 discontinuities. This graph has no zeros. And I'm going to test around those numbers. Now, 4 is where the graph has this vertical asymptote. So I'm going to say D and E. And I'm going to test only here because that was our mission. So I'll pick a number between 1 and 4 to put into my equation. Now, I think that the ideal place to put it would be in the factored form. So number between 1 and 4, put a number in like 3. So 3 minus 1 is 2 times -1. So I have a negative numerator over negative times positive. 2 negatives means I have a positive output. Now we pick a number bigger than 4. So a number bigger than 4, I would, in my numerator, I would have a negative over positive times positive, odd number of negatives, negative output. So the limits around the asymptote can be written as the limit as x approaches 4 from the left, f of x is going to show positive unbounded behavior, and the limit as x approaches 4 from the right-hand side would show negative unbounded behavior. Now remember, all of these limits technically do not exist because in order to exist, it has to approach a defined value. Last one here, we have, it's already factored for us, we have a vertical asymptote at x equals 2. Now, that is the only number that we would put on a sign chart because we have no zeros, no holes, or anything else like that. So I put 2 on that sign. I put 2 on that sign chart, and I'm going to plug in numbers around it. So if I put in 0 for x, 3 over -2 squared, positive. Put a number bigger than 2, 3 over number bigger than 2 minus 2 squared, also positive. So both sides of this function, as you approach 2, are going to display the same kind of unbounded behavior. This is an example of where I could actually write the two-sided limit because both sides showed the same kind of behavior and say the two-sided limit is positive infinity. Now remember, these limits technically do not exist, but we can write them as being set equal to positive or negative infinity just to describe the kind of unbounded behavior. Now let's find some limits from the graphs. So part A here, let's find f of 0. So f of 0, I'm looking here graphically, I want to find out where the function is defined at 0, and it's defined right here at negative, y equals -1. So A, f of 0, -1. For B, find the limit as x heads towards negative infinity. So as x heads towards negative infinity, I just keep going off to the graph to the left to see what am I approaching. And I'm going to assume here with the way it's flattening out that it's going to just flatten out at -2. We'll say -2 is the horizontal asymptote. Now let's look at the right-hand side. So as x heads towards positive infinity for part C, what is the graph doing? It's a head way off here to the right. It looks like it's leveling off. We're going to get very close to the x-axis. So we'll say that limit equals 0. Part D, the limit as x approaches 2 from the right-hand side. So here's 2, vertical asymptote. From the right-hand side, the graph is increasing when outbound. So we'll say equals positive infinity. Part E, as x approaches 2 from the left-hand side, so 2 still that vertical asymptote, values to the left of 2, work my way back to it, decreasing when outbound, we'll say equals negative infinity. Lastly, part F, what is f of 2? I'm looking at 2, the function is defined nowhere, so we'll say undefined or does not exist.